Okay, so let's do a graph of this one. Now, we know that it's got 4 intersections, right? Okay, -1, okay, -3, and 1, and 3. Now, you can't really tell which direction it's pointing. Okay, is it a W or an M? Are the ends pointing up or down?
W.
Right, it is a W. Okay, good, because it's positive. It's +4. The ends are going to point up. So even though you can't tell very good on the graph, it is going to look like this. Okay, and mine is not perfect by any means. Okay, you don't have to be. That's just a sketch. But we can tell because this 4 is positive, it's pointing upwards. Okay, just like this one is a positive x squared, the ends are pointing upwards. Okay, we'll do one more like this and then just 2 more of a different type of problem. Okay, but none of it's very complicated. This one's number 5. -2x to the 4th power plus 16x squared minus 32 equals 0. Okay, -2x to the 4th power plus 16x squared minus 32 equals 0. Okay, we'll do this one together because it's kind of special, and I want to point out something to you. Okay, first of all, how many solutions? 4, right? So the 4th power. Okay, is it going to be a W like this, or is it going to be upside down like an M? Upside down. All right, it's going to be, because it's negative. This one's negative. It'll be upside down. The ends will be pointing downward. Good. So let's put it in the calculator and look. -2x to the 4th power plus 16x squared minus 32. Okay, look what it looks like. Okay, it does look like it's going to be an M, right? But how many solutions does it look like there are? 2, right? It looks like there's one right there and one right there. Okay, this one's kind of like number 1 on the front, where we had the repeating solution where it touches it and turns right back around and goes in the other direction. Okay, this is going to have that twice. Okay, you can still use second trace 5, enter, 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 and it's going to do this thing that I remember talking to y'all about last semester. Okay, if it has a repeating 0, for whatever reason, it gives you this funny decimal, 2.0000005. Okay, well, 2.00005 is 2, right? But for some reason, when it has more than one solution there and it just touches and turns back around, it gives me a funny decimal. That's kind of a one way of knowing that, oh, there's 2 solutions there. Okay, so this is a repeating one. X equals 2, x equals 2. That one's twice because it goes up and turns right back around and comes back down. Okay, then same thing on the other side. Second trace 5, and I'm going to move it over. Okay, I think I know that that's at -2. See, kind of the same thing. It did a funny decimal. -1.9999999 is what? -2, right? For whatever reason, whenever it is a repeating or a double solution, it gives you a decimal. And I don't know why. It's just a glitch on the calculator, but it's kind of helpful because it tells me, okay, what's at -2? X equals -2. Okay, so these are both repeating. And the way that looks on the graph is that it just goes up and touches and comes right back down. Okay, so even though there's only 2 unique solutions, -2 and 2, there really are 4. There's just 2 in one place and 2 in the other. Okay, so these are both repeating. That's what you call it, I believe. That's what we always called it. This one's repeating. That's why it's the same. Just because I know you expect to see 4. Right, and there are 4 parts. It's a quartic, you can tell, because it's shaped like an M. There's just 2 here and 2 there. Okay, and the last part is going to be that little white sheet of paper. We can glue this into our notes whenever we're done with the notes, okay? So you don't need to glue it in right now. Okay, it's a theorem called the rational root theorem. Okay, here's the deal. When I was in school even, we didn't have calculators we weren't allowed to use them until calculus. But even, I think they were still like pretty new. Like it was a new cool thing, graphing calculators. Before that, to find the roots, they would have to, I don't even think that they knew the cool way of factoring that we knew. I don't remember knowing how to factor the way we do. What we had to do was kind of guess what we thought the answer would be and try to work it out backwards and see if we were right. Okay, so we kind of had to do trial and error. So that's kind of what the rational root theorem is coming from. It's a way to help you narrow down what the answers could be. Okay, it's potential rational zeros. This is a formula that helps you figure out what they could be. Okay, and it's a fraction. Okay, the factors of the constant divided by the factors of the leading coefficient. Okay, so the constant is going to be called P. Okay, P divided by Q. Okay, P divided by Q. And when you're in the problem, it's going to be the last number. The constant is the number that's a number. Okay, that doesn't have a variable. Okay, it's constant. It doesn't vary. It doesn't change. So that would be P is always going to be the last number. Okay, constant. It's a number. Right, and the Q is always going to be the lead coefficient, the first number. Right, just like when we do factoring, we do A times C, the first number times the last number. Those are the two numbers that determine what's going on in the middle and what the solutions are. Okay, that's why we do A times C when we're trying to find the factors. Okay, so it's P factors of P on top and factors of Q on the bottom. Okay, so in this case, our P is 7.